Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should truly make your mind expand. Perhaps so much that it naturally drifts off into the cosmos. Imagine our Earth, with its solid ground beneath your feet, its oceans, its mountains, all cradled by a relatively thin, breathable atmosphere. Now imagine a world so vast that you could fit over 1/300 Earths inside it. Not just conceptually, but physically. A world so immense that its mass is more than twice the mass of all the other planets in our solar system combined. This isn't some distant exoplanet. This is Jupiter, our solar system's colossal guardian, silently orbiting just a few 100 million miles away. But here's the truly mind-bending part. Despite its staggering size and mass, there's no solid ground to stand on. No firm surface, no stable crust, no place where you could plant a flag and say, quote, "If you tried to descend into Jupiter, you wouldn't crash onto a rocky landscape. You would simply fall deeper and deeper through ever denser layers of gas and exotic liquids, until the pressure and temperature would crush and vaporize any known material. It's a planet that is, in essence, a giant spinning ball of fluid, a cosmic paradox where, quote 1 and quote 2, become less about gravity and more about density." This profound difference from our home world isn't just a curiosity. It fundamentally reshapes everything we understand about planetary formation, atmospheric dynamics, and even the very nature of matter under extreme conditions. It's a universe of wonder right next door. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with a thought experiment that sounds simple, but quickly unravels into profound strangeness. Imagine you're an astronaut, equipped with the most advanced spacecraft humanity could ever build, and your mission is to land on Jupiter. What does that even mean? On Earth, landing means touching down on solid ground. On the Moon, it was a dusty, cratered surface. Even on Mars, it's a rocky red landscape. But on Jupiter, or Saturn, or Uranus, or Neptune, there is no such thing as a saggy, quote, 4 in the way we understand it. There's no definite boundary where the atmosphere ends and solid ground begins. Instead, these planets are fluid worlds, their gaseous outer layers seamlessly transitioning into liquid and then into even more exotic states of matter, all without ever encountering a distinct solid phase. This isn't just a minor detail, it's a fundamental characteristic that dictates everything about these colossal worlds, from their internal dynamics to their powerful magnetic fields, and it challenges our very terrestrial intuition about what a quote can be. To truly grasp this, we need to redefine what we mean by quote when we're talking about a planet like Jupiter. When you think of gas, you probably imagine the air around you, mostly nitrogen and oxygen, relatively transparent, easy to move through. But on Jupiter, the gas is overwhelmingly hydrogen and helium, the two lightest and most abundant elements in the universe. And crucially, this gas isn't confined to a thin shell. It makes up the vast majority of the planet's entire volume. As you descend into Jupiter, the pressure from the immense weight of the overlying atmosphere increases exponentially. On Earth, atmospheric pressure at sea level is about 1 bar. At Jupiter's Chat-9, the arbitrary point scientists define as its quotus 10 for reference, even though it's still deep in the gas, the pressure is already crushing, but it doesn't stop there. The deeper you go, the more material is above you, pushing down with unimaginable force. This escalating pressure does something extraordinary to matter. Gases, when compressed enough, don't just get denser, they undergo phase transitions. They can become liquid, or even a supercritical fluid, a state where there's no clear distinction between liquid and gas. Imagine trying to swim in an ocean where the water gradually becomes less like water and more like a very thick, soupy air, then even denser until it's more like a viscous syrup, but it's still a fluid. On Jupiter, this transition happens continually. The molecular hydrogen that forms the bulk of its outer layers gradually compresses into a liquid state. This isn't a sudden change you could point to like the surface of an ocean. It's a continuous gradient. You wouldn't splash into it. You'd simply find yourself moving through an increasingly viscous, opaque, and incredibly hot fluid, with the weight of an entire world pressing down on you. The scale of this pressure is almost impossible to visualize. Consider the deepest part of Earth's oceans, the Mariana Trench, where pressures reach about 100 times that at sea level. That's enough to crush most submarines. On Jupiter, just a few thousand kilometers down, the pressure can reach millions of times Earth's atmospheric pressure. Under such extreme conditions, hydrogen, which we know as a gas, behaves in ways that are utterly alien to our everyday experience. The electrons, usually bound to their individual protons in hydrogen molecules, start to become delocalized, meaning they're no longer tied to a specific atom. They're free to move, much like electrons in a metal. This creates a bizarre substance known as metallic hydrogen. Metallic hydrogen is theorized to exist deep within Jupiter and Saturn, and it's a phase of matter that doesn't occur naturally anywhere on Earth, except fleetingly in highly specialized, incredibly high-pressure laboratory experiments. Imagine hydrogen, the lightest element, behaving like a liquid metal, electrically conductive, dense, and flowing. This isn't a solid core, it's a vast churning ocean of metallic hydrogen, making up a significant portion of the planet's interior. This layer is responsible for generating Jupiter's incredibly powerful magnetic field, a topic we'll delve into later. The sheer volume of this exotic material is staggering. It's estimated to extend for tens of thousands of kilometers, far deeper than Earth's entire diameter. So, when we talk about landing on Jupiter, we're not just talking about falling through gas. We're talking about descending into a realm where the very laws of chemistry and physics, as we experience them, are bent and reshaped by pressures and temperatures that defy imagination. There is no floor, only an endless, deepening descent into progressively denser, more exotic states of matter, until the very concept of distinct phases blurs into a continuous, overwhelming gradient. We left off contemplating Jupiter's profound secret, a vast churning ocean of liquid metallic hydrogen, an utterly alien substance, roaring through its interior under unimaginable pressures. This isn't just a fascinating exotic material, it's the very heart of Jupiter's power, the engine that drives one of the most astonishing phenomena in our solar system, its colossal magnetic field. Imagine, if you will, a planet so immense, so dynamic, that its entire core functions like a colossal, self-sustaining dynamo. We're not talking about a small, localized magnetic anomaly here. Jupiter's magnetic field is a truly staggering force, a cosmic paradox in itself. It's nearly 20,000 times stronger than Earth's, extending millions of miles into space, far past the orbits of its largest moons. What does that even mean for a planet? For one, it means Jupiter is encased in an invisible protective bubble called a magnetosphere, a vast region where the planet's magnetic field dominates over the solar wind, the constant stream of charged particles emanating from the Sun. On Earth, our magnetosphere is vital. It deflects most of these harmful particles, preventing our atmosphere from being stripped away and shielding us from radiation. Jupiter's magnetosphere does the same, but on a scale that beggars belief. But here's where the paradox deepens and the quotius 13 Nielsen becomes a different kind of danger. While Jupiter's magnetosphere does deflect the solar wind, it also traps an incredible amount of charged particles, accelerating them to mind-bending speeds. These particles, primarily electrons and ions, form intense radiation belts around Jupiter, far more powerful and deadly than Earth's Van Allen belts. If you were to venture anywhere near Jupiter without heavy shielding, these radiation belts would deliver a lethal dose in minutes. This is a crucial detail they certainly didn't teach us in school. Jupiter, while a majestic protector of its own, is also a silent, incredibly powerful killer for any unprepared visitor. It's a beautiful, violent world, a testament to the extreme forces at play in our universe. This immense magnetic field, born from the churning metallic hydrogen, is also responsible for Jupiter's spectacular auroras. On Earth, our polar lights shimmer with greens and reds, a beautiful dance in the night sky. Jupiter's auroras are 1,000,000 times more powerful, a constant blazing inferno of ultraviolet light, visible only to specialized instruments, forming rings larger than our entire planet around its poles. They are a direct, dazzling manifestation of the energy being funneled down by that incredible magnetic field, exciting atmospheric gases into a perpetual light show. It's a visceral reminder that this giant isn't just a big ball of gas. It's a living, breathing, electrically charged entity. Now, let's revisit that idea of a giant spinning ball of fluid. This isn't just a poetic description, it's the fundamental reality that shapes everything we see and don't see about Jupiter. Unlike Earth, which rotates as a solid body, mostly, Jupiter, being primarily fluid, exhibits a phenomenon called differential rotation. Imagine trying to spin a giant blob of jello. The middle might spin faster than the edges, right? That's essentially what happens on Jupiter. Its equator spins incredibly fast, completing a rotation in just under 10 hours, while its polar regions take about 5 minutes longer. This might not sound like much, but on a planet this enormous, that difference creates staggering shear forces, profoundly influencing its atmospheric dynamics. This rapid differential rotation also has a visible effect on Jupiter's shape. Have you ever noticed how Jupiter, in images, looks a little squashed, like a slightly deflated basketball? That's not an optical illusion, it actually is squashed. Because it's spinning so fast and is composed almost entirely of fluid, the centrifugal force at its equator is immense, causing it to bulge outward. Its equatorial diameter is about 8,500 miles greater than its polar diameter. Earth has a tiny equatorial bulge too, but it's barely noticeable because our planet is mostly solid and spins much slower. Jupiter's oblateness is a profound visual cue to its fluid, rapidly rotating nature. It's literally being stretched and flattened by its own immense spin. And what about that atmosphere? What does it look like to have an entire planet in perpetual churning motion? From our telescopes, Jupiter is a masterpiece of swirling colours, bands of cream, orange, brown, and red, punctuated by enigmatic spots and streaks. These aren't just pretty patterns, they are the visible manifestations of colossal weather systems, driven by the planet's internal heat, its rapid rotation, and the constant flow of its fluid interior. Those distinctive bands we see are called zones and belts. The lighter, brighter zones are regions where warm gases are rising, bringing ammonia ice crystals to higher altitudes, making them appear white. The darker reddish-brown belts are where cooler gases are sinking, carrying chemicals from deeper layers to slightly lower altitudes, where they react with sunlight to produce their characteristic hues. Between these rising and sinking currents, powerful jet streams scream across the planet at hundreds of miles per hour, often in alternating directions. Think about that for a moment. An entire planet covered in parallel, opposing currents of gas, like an endless series of colossal conveyor belts. This is not just wind. This is an entire planetary atmosphere in a state of constant, furious motion, sculpted by the Coriolis effect, which is incredibly powerful on a fast-spinning fluid world. On Earth, the Coriolis effect helps create hurricanes and deflects ocean currents. On Jupiter, it organizes the entire atmosphere into these distinct, long-lived bands. And then, of course, there's the Great Red Spot. This iconic feature is perhaps the most famous storm in the entire solar system, a colossal anticyclonic vortex that has been raging for at least 350 years, and possibly much longer. It's so immense that Earth could comfortably fit inside it, perhaps even 3 times over. Imagine a storm on Earth that never dissipates, a hurricane that has been churning for centuries, its crimson eye staring out into the cosmos. That's the Great Red Spot. Why does it persist for so long? On Earth, hurricanes eventually run out of energy when they hit land or move over cooler waters. But Jupiter has no solid surface to break up the storm, and no distinct ocean to cool it. It's a fluid world, and the Great Red Spot, along with countless other smaller vortices, simply rolls along within those powerful parallel jet streams like a massive eddy in an unimaginably vast river. It's a testament to the sheer scale and longevity of atmospheric phenomena possible on a gas giant. These storms are not just weather, they are semi-permanent features of the planetary landscape, continually merging, shrinking, and growing, but always present. When we consider Jupiter, we are truly looking at a world that challenges our most basic terrestrial assumptions about what a planet is. It's not a solid sphere with a surface to stand on. It's a swirling, radiating, dynamically evolving system, a cosmic dynamo generating an awe-inspiring magnetic field, a fluid sphere bulging at its equator, and an atmosphere of perpetual monumental storms. It's a vibrant, dangerous, and utterly captivating testament to the sheer diversity of worlds within our own solar system. And it makes us wonder, what else about these giants is so profoundly different from our earthbound experience? What other secrets do they hold that require us to completely redefine our understanding of planetary physics, we've only just begun to scratch the surface of their profound strangeness. We've peered into the swirling depths of Jupiter's atmosphere, marvelled at the timeless fury of the great red spot, and even imagined a descent through its increasingly dense layers, eventually reaching that bizarre, churning ocean of metallic hydrogen. But what lies beyond that? What truly makes this colossal world tick? If Jupiter challenges our very definition of a planet from its atmosphere down to its metallic heart, then what secrets does its ultimate core hold? Prepare yourselves, because the journey inward continues, and it's about to get even more mind-bending. We've established that Jupiter lacks a solid surface in the way Earth does. There's no crust, no mantle, no distinct boundary where rock ends and atmosphere begins. Instead, it's a gradual, continuous transition. But deep, deep within, far beneath the metallic hydrogen ocean, the pressures and temperatures become so extreme that even our most advanced models struggle to paint a clear picture. We're talking about pressures millions of times greater than Earth's atmospheric pressure at sea level, and temperatures that rival the surface of the Sun, tens of thousands of degrees Celsius. What does matter look like under such conditions? For a long time, the prevailing scientific hypothesis suggested that Jupiter harboured a dense, rocky core, perhaps Earth-sized or even larger, composed of silicates and iron, the same heavy elements that make up our own planet's interior. This core accretion model proposed that Jupiter started as a rocky embryo, gradually accumulating more and more gas from the protoplanetary disk around the young Sun, until it ballooned into the behemoth we see today. However, recent observations, particularly from the Juno spacecraft, are challenging this neat picture. It seems Jupiter's core might not be a distinct solid ball at all. Instead, it could be a fuzzy core, a diffuse region where heavy elements are not neatly concentrated, but rather partially dissolved and mixed into the metallic hydrogen layer above. Imagine dropping a sugar cube into a giant cup of coffee. It doesn't just sit at the bottom as a distinct cube, but slowly dissolves and disperses throughout the liquid. Jupiter's core might be doing something similar, a vast, swirling mix of heavy elements and metallic hydrogen, where the boundaries are blurred and indistinct. This fuzzy core hypothesis is a testament to the profound strangeness of gas giants. It means that even at its very heart, Jupiter defies our terrestrial intuition. There's no solid ground to stand on, not even in principle. It's a giant spinning ball of fluid and plasma all the way down. This incredible internal heat, generated by the planet's slow contraction and the gravitational settling of heavier elements, is so immense that Jupiter actually radiates more energy into space than it receives from the Sun. It's a subtle, internal furnace, a constant, slow burn that contributes to its dynamic weather and fuels its powerful magnetic field. But how did such an utterly alien, self-heating, gravitational behemoth come into being? The story of Jupiter's formation is as dramatic and pivotal as the planet itself, and it casts Jupiter not just as a planet, but as a cosmic architect that profoundly shaped our entire solar system. In the swirling, chaotic early days of our solar system, about 4.5 billion years ago, the Sun was just a newborn star, surrounded by a vast disk of gas and dust, the protoplanetary disk. This was the cosmic nursery where all the planets were born. Jupiter, we believe, was the first true giant to emerge under the traditional core accretion model, a solid, icy and rocky core, perhaps 10 times the mass of Earth, formed relatively quickly. Once this core reached a critical mass, its immense gravity began to furiously snatch up vast quantities of hydrogen and helium gas from the surrounding disk like a cosmic vacuum cleaner. It grew exponentially, swelling to its current colossal size in what, cosmically speaking, was a blink of an eye, perhaps just a few million years. Another hypothesis, called the disk instability model, suggests an even faster formation. In this scenario, dense clumps of gas and dust in the protoplanetary disk could have collapsed directly under their own gravity, bypassing the need for a solid core to form first. Whichever mechanism was at play, the result was the same: a planetary titan, a gravitational anchor that would go on to profoundly influence the destinies of its smaller siblings. Jupiter didn't just passively grow into existence. It was an active participant, a mover and shaker in the early solar system's tumultuous dance. One of the most compelling theories about Jupiter's early life is the one, quote 18 Joua hypothesis. Imagine Jupiter, having formed further out, then migrating inward towards the Sun, clearing a wide swathe through the protoplanetary disk. This inward journey would have scattered planetesimals, the building blocks of planets, sending some crashing into the Sun, others careening outwards. Then, influenced by the formation of Saturn, Jupiter reversed course, quote 19, back outward to its current orbit. This grand migration, this planetary slingshot maneuver, had staggering consequences. It's theorized that Jupiter's inward movement pushed a vast amount of material into the inner solar system, contributing to the formation of the terrestrial planets, Mercury, Venus, Earth, and Mars. But its outward, quote 20, might have been just as impactful, scattering the remaining planetesimals in the inner solar system, preventing Mars from growing as large as Earth or Venus. Some models suggest that without Jupiter's influence, Mars might have been a much larger, Earth-like world. Jupiter also played a pivotal role in the creation of the asteroid belt, that vast donut-shaped region between Mars and Jupiter. Instead of allowing the rocky debris there to coalesce into another planet, Jupiter's immense gravitational influence stirred up the planetesimals, preventing them from ever fully forming a coherent body. It's like a cosmic bully breaking up a construction project before it can even begin, leaving behind a field of shattered remnants. And its influence didn't stop there. Jupiter continues its role as the solar system's gravitational gatekeeper and protector. Its immense mass and powerful gravity act as a cosmic vacuum cleaner, deflecting or absorbing countless comets and asteroids that might otherwise pose a threat to the inner planets, including Earth. We see evidence of this protective role regularly, as Jupiter is struck by comets and asteroids far more frequently than Earth, leaving transient scars in its atmosphere. The famous Shoemaker-Levy 9 comet impact in 1994, which tore apart and slammed into Jupiter's atmosphere over several days, was a dramatic, real-time demonstration of this planetary defense mechanism. Yet, this protection comes with a caveat. While Jupiter often clears out dangerous debris, its gravity can also, paradoxically, sling objects inward towards the inner solar system, or even eject them entirely from the solar system, depending on the specifics of the gravitational interaction. It's a complex, dynamic dance, where Jupiter acts as both guardian and occasional instigator. So when we talk about Jupiter, we're not just discussing a planet, we're talking about a fundamental component of our cosmic neighborhood, a gravitational linchpin that shaped the very architecture of our solar system. Its sheer scale and profound influence force us to continually redefine our understanding of what a quote 21 truly is. Is Jupiter merely a giant planet, or is it something more? With its internal heat generation, its predominantly hydrogen and helium composition, and its immense gravitational field, Jupiter shares more characteristics with the star than with Earth. It's often referred to as a failed star, a celestial body that gathered nearly enough mass to ignite nuclear fusion in its core, but not quite. If Jupiter were about 80 times more massive, its core would have reached the temperatures and pressures necessary to kickstart fusion, and our solar system would be a binary star system. This comparison isn't meant to diminish Jupiter's planetary status, but rather to highlight its utterly unique position. It exists in a fascinating limbo, a grand experiment in planetary physics that pushes the boundaries of our imagination. It's a world without a surface, a churning sea of exotic matter, an internal furnace, and a gravitational architect all rolled into one. We've barely scratched the surface of Jupiter's profound strangeness. We've explored its fiery heart, its ancient birth story, and its role as a cosmic sculptor. But what about the worlds that orbit Nisand? What about the miniature solar system of moons that dance in its powerful gravitational embrace, each a unique and fascinating world in its own right? Some of them harbouring secrets that could redefine our understanding of where life might exist beyond Earth. Our journey through the gas giants is just beginning, and the wonders only continue to grow. Next, we'll turn our gaze to those captivating companions, beginning with the Galilean moons, each a testament to Jupiter's colossal influence, and each a world waiting to reveal its own astonishing story. Prepare for another shift in perspective, because around Jupiter even the moons are extraordinary. We've journeyed deep into the stormy heart of Jupiter itself, unravelling its liquid metallic core, its colossal magnetic field, and its role as a cosmic architect. We've seen how this gas giant, almost a failed star, utterly redefines what a just quote 93 can be. But Jupiter isn't alone out there, floating in the vast cosmic ocean. It's the sun of its own miniature solar system, a gravitational titan orbited by a retinue of moons, 4 of which stand out as worlds of profound strangeness and staggering scientific potential. The Galilean moons. When Galileo Galilei first turned his rudimentary telescope towards Jupiter in 1610, he saw 4 tiny pinpricks of light dancing around the giant planet. He didn't know it then, but he was observing worlds that would challenge our most fundamental assumptions about where life might arise and how planetary bodies truly work. These aren't just inert rocks, they are dynamic, active, and in some cases surprisingly Earth-like, at least beneath their frigid exteriors. Their existence, their very vitality, is a direct testament to Jupiter's overwhelming gravitational power. It's a cosmic dance of immense forces, where the sheer bulk of the gas giant kneads and flexes its moons, generating internal heat through a process we call tidal heating. Imagine squeezing a stress ball over and over again. It warms up, right? Now scale that up to planetary proportions, with Jupiter as the giant cosmic hand, and you begin to grasp the engine driving these incredible worlds. Let's dive into these 4 unique satellites, starting with the innermost and arguably the most extreme. Io. If you thought Jupiter was a wild ride, Io is a truly hellish landscape, a perpetual volcanic inferno. This moon is often described as the quote 24 because its surface is stained with vibrant yellows, oranges, and reds from sulfur and sulfur dioxide, constantly spewed forth by hundreds of volcanoes. We're not talking about a few active volcanoes like on Earth. We're talking about a world where volcanic eruptions are the default state. Plumes of material shoot hundreds of miles into space, raining down fresh sulfur snow and lava flows that rapidly resurface the entire moon. In fact, Io is the most volcanically active body in the entire solar system. Why such extreme activity? It all comes back to Jupiter's gravitational embrace. Io is locked in a gravitational tug-of-war, not just with Jupiter, but also with its fellow Galilean moons, Europa and Ganymede. As Io orbits Jupiter, it's constantly pulled and stretched, first one way, then another, by the combined gravitational forces. This constant flexing generates immense friction deep within its interior, heating it to incredible temperatures. It's like the moon is perpetually undergoing a deep tissue massage from Jupiter, but instead of relaxation, it results in molten rock bursting through its crust. The surface of Io is a mesmerizing, terrifying spectacle of constant change, a stark reminder of the raw, untamed power of the cosmos. No solid surface here for long, just endless rivers of lava and towering volcanic plumes under a sky of Jupiter's omnipresent glow. From Io's fiery chaos, we move to a world that offers perhaps the most tantalizing prospect for life beyond Earth: Europa. This moon, slightly smaller than Earth's moon, is encased in a shell of water ice, crisscrossed by an intricate network of cracks and ridges that look, from orbit, like veins on a marble. For decades, scientists suspected something profound lay beneath that frozen crust, and indeed, the evidence has now become overwhelming. Europa harbours a vast global ocean of liquid water, potentially twice the volume of all of Earth's oceans combined. How do we know there's an ocean beneath a miles-thick ice shell? The clues are fascinating. When the Galileo spacecraft flew past Europa, it detected a magnetic field that seemed to fluctuate in response to Jupiter's own powerful magnetosphere. This phenomenon, called magnetic induction, is exactly what you'd expect if there were a large electrically conductive body, like a salty ocean sloshing beneath the ice. Further observations, including tantalizing evidence from the Hubble Space Telescope, have even hinted at plumes of water vapor erupting from Europa's south polar region, much like geysers on Earth, offering a potential direct sample of its subsurface ocean. This isn't just any ocean. It's an ocean kept liquid by the same tidal heating mechanism that tortures Io. Europa's gravitational flexing, though less extreme than Io's, still provides enough internal warmth to prevent the water from freezing solid. And here's where it gets truly exciting for astrobiology. Scientists believe that at the bottom of Europa's ocean there could be hydrothermal vents, similar to those found in Earth's deep oceans. On Earth, these vents spew out superheated, mineral-rich water, creating vibrant ecosystems teeming with life that thrives in total darkness, powered by chemical energy rather than sunlight. Imagine alien microbes, perhaps even more complex organisms, flourishing in Europa's lightless depths, sustained by the very geological activity driven by Jupiter. It's a profound thought, isn't it? A world where life could exist, utterly alien to our surface-dwelling experience, yet perhaps fundamentally similar in its chemical needs. Future missions like NASA's Europa Clipper and ESA's JUICE are designed to explore this enigmatic ocean world, searching for signs of habitability and perhaps even life itself. Next in line is Ganymede, the largest moon in our solar system. In fact, Ganymede is so big that it's larger than the planet Mercury and nearly 3/4 the size of Mars. If it orbited the Sun directly, it would easily be classified as a planet. But its size isn't its only claim to fame. Ganymede holds a unique distinction among moons. It possesses its own intrinsic magnetic field. Think about that for a moment. Only Earth, Mercury, and the gas giants in our solar system have their own self-generated magnetic fields. For a moon to have one suggests something extraordinary beneath its icy rocky surface. It implies a molten, convecting iron core, much like Earth's, generating a protective bubble against the harsh radiation environment of Jupiter. This active dynamo is yet another testament to the internal heat generated by tidal forces, albeit less intensely than on Io or Europa. Like Europa, Ganymede is also believed to harbour a vast subsurface ocean, but potentially with a more complex structure. Evidence suggests there might be multiple stacked layers of ice and liquid water, perhaps even separated by layers of different phases of ice, due to the immense pressures involved. Imagine descending through a frozen crust into a liquid ocean, then through another layer of ice and another ocean, before finally reaching a rocky seabed. It's a truly mind-bending concept, a multi-layered water world of staggering complexity. Ganymede's surface also tells a story of geological activity, with distinct regions of ancient, heavily cratered terrain, alongside younger, grooved terrain created by tectonic forces. It's a world that has seen immense change over billions of years, a testament to its internal dynamism. Finally, we arrive at Callisto, the outermost of the Galilean moons. In many ways, Callisto is the quiet elder sibling of the group. Its surface is the most heavily cratered of the four, a stark ancient canvas preserved since the early days of the solar system. Unlike its inner neighbours, Callisto shows very little evidence of significant geological activity on its surface. This is because its greater distance from Jupiter means it experiences far less tidal heating. It's not locked in the same intense gravitational dance as Io, Europa, and Ganymede, so its interior has remained relatively cold and inactive. However, even Callisto holds a surprise. Despite its ancient, seemingly inert surface, data from the Galileo spacecraft suggests that it too might possess a subsurface ocean. This ocean, likely deeper and more isolated from a rocky core than Europa's, would be encased within a shell of ice and rock, making it less likely to harbour the same kind of hydrothermal vent activity. But the mere presence of liquid water, even on this seemingly dead world, underscores a profound truth. Water, the elixir of life, might be far more common in our solar system than we ever imagined. Callisto's stable, less radiated environment, compared to its inner siblings, also makes it an intriguing candidate for a future human outpost, a potential staging ground for exploring the rest of the Jovian system. What we learn from these four incredible moons is a fundamental redefinition of planetary habitability. We tend to think of life needing a star for energy, but here Jupiter acts as a secondary energy source, its immense gravity providing the warmth needed to melt ice and drive geological processes. These moons are miniature, diverse worlds, each a testament to the powerful influence of their gas giant parent. They are not merely cold, dead rocks. They are dynamic, evolving bodies, some of which hold the most compelling evidence for extraterrestrial life in our cosmic backyard. This journey through Jupiter's domain, from its swirling clouds to its fuzzy core, and now to its extraordinary moons, forces us to shed our terrestrial biases. We're exploring systems that operate on scales and with physics utterly alien to our everyday experience. The gas giants, far from being simple, featureless spheres, are cosmic powerhouses, architects and incubators of potential life. They are the true wild frontiers of our solar system, challenging us to expand our understanding of what's possible, what's out there, and what life itself might truly mean. We've just begun to scratch the surface of their profound strangeness, and the more we learn, the more we realize just how much more there is to discover. While Jupiter's immense gravity sculpts and energizes its diverse family of moons, proving that habitability can manifest in ways utterly alien to our terrestrial assumptions, it is but the first magnificent chapter in our gas giant saga. We've redefined what a Cassine Quote 26 mind can be, challenged our notions of Dan's Quote 27 and Quote 28, and glimpsed the potential for life in the most unexpected corners of our solar system. But Jupiter, for all its colossal grandeur, is not alone. It's time we journeyed further to meet its equally enigmatic siblings, each one a cosmic paradox waiting to unravel our preconceived notions about planets. Just a little farther out, a shimmering jewel awaits us, a world so iconic it's instantly recognizable even to the most casual observer: Saturn. If Jupiter is the solar system's king, then Saturn is its crowned monarch, adorned with a breathtaking halo of rings. But what they didn't teach you in school is that these rings are not solid, not some ancient static relic. Oh no! They are a dizzying dynamic ballet of countless icy particles ranging from microscopic dust grains to house-sized boulders, all orbiting Saturn with intricate precision. Imagine trillions upon trillions of tiny moons, each following its own path, collectively forming a structure so thin it would vanish if turned edge-on. These rings stretch hundreds of thousands of miles across, yet are often no more than a few tens of feet thick. It's a cosmic balancing act, a celestial dance performed by a planet that, like Jupiter, is fundamentally a giant spinning ball of fluid. Saturn too lacks a solid surface. Descend into its atmosphere, and you'd plunge through layers of increasingly dense hydrogen and helium, eventually reaching a churning ocean of metallic hydrogen, albeit one that begins deeper and is less extensive than Jupiter's. Its atmosphere, though less dramatically banded than Jupiter's, still showcases powerful storm systems, driven by internal heat and rapid rotation. But its true marvels extend beyond its glorious rings. Saturn, like Jupiter, hosts a miniature solar system of its own, with a retinue of moons that are in their own right as astounding and unique as Jupiter's Galileans. Let's talk about Titan, Saturn's largest moon, and a world of profound strangeness. From a distance it appears as an orange orb, shrouded in a thick nitrogen-rich atmosphere, the only moon in our solar system to boast such a substantial gaseous envelope. This atmosphere is eerily reminiscent of early Earth, a hazy cocoon that shields a surface unlike any other. What they didn't teach you is that beneath that orange veil lies a world with an active hydrological cycle, complete with clouds, rain, rivers, lakes, and even seas. The catch? The liquid isn't water, it's liquid methane and ethane, substances that are gases at Earth temperatures but flow like water in Titan's cryogenic environment, where surface temperatures hover around 290 degrees or 179 dong. Imagine standing on the shore of a methane lake, the air thick with hydrocarbons, a hazy orange sky above. The rain here is methane, carving river channels and filling vast basins. It's a profoundly alien landscape, yet one that mirrors the familiar processes of Earth's water cycle and the implications. Scientists ponder the possibility of exotic life, not based on water, but on methane as a solvent, thriving in these frigid hydrocarbon-rich seas. Titan challenges our very definition of what constitutes a habitable environment, inviting us to broaden our biological imagination far beyond Earth's warm, wet confines. Then there's Enceladus, another of Saturn's moons, a small icy world that utterly defies expectations. Like Europa, Enceladus hides a global ocean beneath its frozen crust. But here, the evidence literally erupts into space. From prominent, quote, 30s at its south pole, colossal geysers continuously blast plumes of water vapor, ice particles, and organic molecules hundreds of miles into space. The Cassini spacecraft, which orbited Saturn for over a decade, flew through these plumes, directly sampling their composition. It found salts, silica nanoparticles, and complex organic compounds, all ingredients considered essential for life, all originating from a hydrothermal environment at the bottom of a liquid water ocean. Enceladus is a tiny icy beacon, actively demonstrating that moons, warmed not by the distant sun but by the tidal forces of their giant parent planets, can harbour the very conditions we seek for life. It's a stark reminder that the universe is far more creative than our terrestrial imaginations allow, and that the energy of a giant planet's gravity can be a potent engine for biological potential. As we venture even farther from the Sun, beyond the magnificent rings of Saturn, we encounter two more colossal worlds, Uranus and Neptune, often lumped together with Jupiter and Saturn as gas giants. These two are, in fact, a different breed entirely, the ice giants. What's the distinction? While Jupiter and Saturn are predominantly hydrogen and helium, Uranus and Neptune contain a much higher proportion of, quote, 33, water, methane and ammonia, which behave as fluids under the extreme pressures and temperatures of their interiors. They are smaller than Jupiter and Saturn, but still vast, each capable of swallowing dozens of Earth's whole. Imagine their internal structure, a relatively small rocky core surrounded by a thick slushy mantle of supercritical fluids, a dense, hot, electrically conductive, dust and, quote, 34 of water, methane and ammonia. It's not quite a gas, not quite a liquid, and certainly not a solid, but a peculiar state of matter that we rarely encounter on Earth. This, quote, 35 volts, mantle is where their unique magnetic fields are generated. Unlike Earth's, Jupiter's, or Saturn's magnetic fields, which are relatively aligned with their rotational axes and centered within the planet, Uranus and Neptune possess highly unusual magnetic fields. They are dramatically tilted, often by as much as 60 degrees from the planet's rotation axis, and significantly offset from the planet's geometric center. It's like someone took Earth's magnetic field, tilted it on its side, then shoved it off-center and let it wobble. This bizarre configuration is a direct consequence of their internal structure, telling us that the dynamo creating these fields operates in that strange, slushy ice mantle, rather than a metallic hydrogen ocean or a molten iron core. Their atmospheres too are distinct. Both Uranus and Neptune appear blue or cyan, a colour imparted by the methane in their upper atmospheres, which absorbs red light. But beneath this placid exterior, these are worlds of extreme weather. Neptune, in particular, boasts the fastest winds in the solar system, raging at speeds exceeding 200 miles per hour, whipping massive storms round its globe. And Uranus, it's the solar system's tilted oddball spinning on its side, with an axial tilt of nearly 98 degrees. This means that for part of its long orbit, one pole points almost directly at the sun, experiencing decades of continuous daylight, while the other endures decades of darkness. Imagine the seasonal extremes on such a world. Even their moons offer further surprises. Neptune's largest moon, Triton, is a cryo-volcanic wonderland, spewing plumes of nitrogen ice and dust hundreds of miles high, indicating ongoing geological activity driven by internal heat. It orbits Neptune in a retrograde direction, suggesting it was likely a captured object from the Kuiper belt, rather than forming in situ. So, here we stand, having journeyed from Jupiter's swirling depths and volcanic moons, through Saturn's glorious rings and hydrocarbon seas, to the icy, tilted and windswept realms of Uranus and Neptune. What have we learned? We've learned that the term quote, 36, as taught in elementary school, barely scratches the surface of these profoundly diverse worlds. Jupiter and Saturn, primarily hydrogen and helium, are true, quote 37, with vast oceans of metallic hydrogen. Uranus and Neptune, with their higher proportion of water, methane and ammonia, quote 38, are more accurately termed, quote 39, with slushy, supercritical fluid mantles. Each of these four giants, though sharing the common trait of lacking a solid surface, is a unique cosmic entity, challenging our Earth-centric definitions of what a, quote, 40 is, how it forms, how it evolves, and even where life might arise. They are not merely bigger versions of Earth, they are fundamentally different classes of celestial bodies, governed by physics and chemistry on scales, and under conditions that push the boundaries of our imagination. They force us to redefine, quote 41, as a spectrum of possibilities, from rocky terrestrial worlds to gas-shrouded behemoths, from water-rich ice worlds to hydrocarbon-laden moons. This profound diversity within our own solar system has staggering implications for our search for exoplanets. If our neighbourhood alone harbours such a rich tapestry of planetary types, what wonders await us in the distant star systems we're only just beginning to explore? The gas and ice giants are not just distant, enigmatic spheres. They are cosmic laboratories, expanding our understanding of planetary science and the potential for life in a universe far more imaginative and wondrous than we ever dared to dream. They are, in essence, the ultimate lessons in humility and intellectual curiosity, reminding us that the cosmos always has more to teach. We've journeyed through the swirling, tempestuous clouds of Jupiter, a colossal marble of banded storms and ancient mysteries. We've marvelled at the dazzling intricate rings of Saturn, a celestial crown spun from countless icy particles, each a tiny moonlet reflecting the distant sun, and we've plunged into the serene icy depths of Uranus and Neptune, twin azure giants shrouded in an ethereal blue, their quietude belying the immense pressures within. Through the lenses of our most advanced probes and keen insights of remote sensing, we've peered beneath the surfaces of their enigmatic moons, discovering not barren rocks, but vibrant, dynamic worlds. Oceans of liquid water hidden beneath Europa's cracked shell. Hydrocarbon seas shimmering under Titan's hazy skies. These revelations have challenged every Earth-centric notion of what constitutes a quote 42-ward world, forcing us to reconsider life's potential in the most unexpected corners of the cosmos. Could life truly thrive in such alien environments? The thought often whispers through the data streams, a profound question that reshapes our understanding of existence itself. But as we stand at the precipice of these profound revelations, a more fundamental question emerges, one that truly wasn't on the curriculum in our early school days, not in the way it resonates with us now. Why are these worlds so utterly different from our own rocky terrestrial home? Why are they giant, spinning balls of fluid, rather than solid ground beneath our feet? Worlds where a spacecraft might simply sink into the depths, never to find purchase. The answer, as with so many cosmic mysteries, lies not in their present state, but in the dramatic, formative story of their birth. To truly understand the gas and ice giants, to grasp the very essence of their being, we need to rewind the clock, not just millions, but billions of years, back to the very nascent moments of our solar system's formation. Imagine, if you will, our sun still a protostar, a nascent star to be, its core just beginning to ignite, surrounded by a vast, turbulent yet exquisitely ordered disk of gas and dust, the protoplanetary disk. This wasn't merely a chaotic swirl, it was a cosmic construction zone, a colossal flat platter of primordial material spanning billions of miles, where planets were slowly, inexorably beginning to take shape. Dust motes, no larger than cigarette smoke, began their long, slow dance towards destiny. This disk, however, wasn't uniform in its composition or its conditions. It had distinct zones, defined by a single, critical factor: temperature. Close to the fiery young sun, radiating immense heat even in its infancy, temperatures were scorching. Here, only the most resilient rocky and metallic materials, silicates, iron, nickel, could condense from the hot gas and hold together in solid form. Water, methane, ammonia, and other lighter compounds remained vaporized, unable to coalesce. This is where Mercury, Venus, Earth, and Mars, our familiar terrestrial planets, began their lives, slowly accreting from these heavier, refractory elements. They grew by countless gentle collisions, tiny dust grains sticking together like static charged lint, forming pebbles, then rocks, then ever larger planetesimals, miniature worlds colliding and merging, sweeping up enough material to become the solid, dense worlds we know and stand upon today. Their atmospheres, if they had significant ones of hydrogen and helium, were largely stripped away by the sun's intense early radiation, a solar wind that scoured the inner system clean, and their own relatively weaker gravity, which couldn't hold onto the lightest gases. It was a slow, deliberate dance of accumulation, a painstaking construction process. But venture further out, beyond what we call the Shifrost line cyst, or sometimes the snow line, and the cosmic recipe fundamentally changed. This invisible boundary, roughly 5 times Earth's distance from the Sun, marked a critical transition, a cosmic threshold where temperatures dipped dramatically. Here the conditions were finally cold enough for volatile compounds like water, methane and ammonia to condense into solid ice grains. Think of it. Not just dust and rock, but ice. Billions upon billions of tiny glittering crystals of frozen water, methane clathrates, and ammonia snowflakes. The sheer abundance was staggering. Water ice, methane ice, ammonia ice. These, quote, 44, were far more prevalent in the protoplanetary disk than the heavier rocky and metallic materials available to the inner planets. It was as if the universe had suddenly opened a new, limitless pantry. This extraordinary abundance of icy building blocks was the true game changer, the pivotal moment that set the stage for the formation of the gas and ice giants. While the inner planets were slowly, painstakingly gathering rocks and metals, the outer regions were a veritable buffet of icy material, a cosmic feast waiting to be devoured. Here, massive cores of rock and ice began to form with incredible speed, accumulating material at a rate unimaginable in the inner system. These cores, far more substantial than anything forming closer to the Sun, perhaps 10 to 20 times the mass of Earth, quickly reached a critical mass. This was the tipping point, the moment their destiny was sealed. And once these supersized, icy, rocky cores formed, gravity, that omnipresent sculptor of the cosmos, took over in a truly spectacular fashion. With such immense gravitational pull, these burgeoning giants began to directly capture the most abundant elements in the protoplanetary disk: hydrogen and helium gas. This wasn't a slow, gradual process, like the accumulation of secondary atmospheres on terrestrial planets, which might involve outgassing from volcanoes over eons. No, this was a runaway gas accretion. Imagine a cosmic vacuum cleaner, a gargantuan gravitational maw, sucking up vast quantities of primordial gas at an accelerating, unstoppable rate. The core's gravity was so immense that it simply pulled in everything around it, like a snowball rolling downhill, growing exponentially larger with every passing moment. This is the fundamental difference. The divergent evolutionary path that separated our solar system's behemoths from its rocky inhabitants. Earth and its rocky siblings formed primarily from rock and metal, then maybe captured a thin gaseous envelope, often later replenished by volcanic activity. Jupiter, Saturn, Uranus, and Neptune, however, first built massive, icy rocky cores, then rapidly engulfed colossal amounts of hydrogen and helium, becoming the gas and ice behemoths we see today. Jupiter, the fastest and most efficient of the lot, a true gravitational glutton, likely reached its current immense size in just a few million years, a blink of an eye in cosmic terms. This rapid, voracious growth explains its overwhelming hydrogen and helium composition, its immense gravitational field, and its undeniable role as the solar system's gravitational patriarch, the undisputed king of the planetary realm. Saturn followed a similar, though slightly less rapid path, its growth possibly hindered by Jupiter's earlier, more aggressive sweeping of available gas. Uranus and Neptune, the ice giants, are slightly different, occupying a distinct category. While they also formed beyond the frost line, their growth might have been slower, or perhaps they formed in a region with less available hydrogen and helium gas, having been somewhat starved by their larger siblings. Their ice giant designation reflects their higher proportion of water, methane, and ammonia, ices, which, remember, behave not as solid ice cubes, but as hot, dense, supercritical fluids in their interiors due to the extreme pressures and temperatures relative to the pure hydrogen and helium dominance of Jupiter and Saturn. They still have hydrogen and helium, of course, forming their outermost layers, but their internal structure is weighted more towards these heavier ice compounds, giving them their distinctive blue-green hues and unique magnetic fields. This early formation history also sheds light on another mind-bending aspect of these worlds, their internal heat. We've discussed how Jupiter and Saturn radiate more heat than they receive from the Sun, an energy output that puzzles many at first glance. This isn't just residual warmth from their formation, like a cooling ember. It's the lingering thermal energy from their colossal gravitational collapse during formation. Imagine the sheer, unimaginable amount of energy released as billions upon billions of tons of gas and ice compressed under their own immense weight, falling inward with incredible force. That primordial heat, trapped within their gargantuan fluid bodies, a relic of their violent birth, is still slowly leaking out, billions of years later, driving much of their internal dynamics, fueling their storms, and powering their powerful magnetic fields. Earth's internal heat, while significant and vital for plate tectonics, comes primarily from radioactive decay and some leftover accretion heat, but it pales in comparison to the scale of the giant's thermal engines, which are truly planetary furnaces, and let's not forget the dynamic, often violent, dance of planetary migration that characterized the early solar system. We touched upon Jupiter's Shastanji's, quote, 40th. In an earlier chapter, a dramatic hypothesis suggesting how it may have migrated inward towards the Sun, then outward again, profoundly shaping the asteroid belt, scattering planetesimals, and even influencing the size and composition of Mars. This wasn't just a static process where planets formed and stayed put. The early solar system was a chaotic, evolving place, a cosmic mosh pit where gravitational forces dictated movements on a grand scale. The giants, through their sheer mass, were not only accumulating material but also gravitationally stirring the pot, scattering planetesimals like marbles, and influencing the orbits and eventual compositions of their smaller neighbours. Some scientists even propose that Uranus and Neptune might have swapped places or migrated significantly further out from their initial formation locations, adding another layer of complexity to their already fascinating story, a testament to the unpredictable nature of cosmic evolution. So, when we look at Jupiter's swirling ancient storms, or Saturn's magnificent ephemeral rings, or the deep blue enigmatic hues of Uranus and Neptune, we are not just observing current weather patterns or beautiful aesthetics. We are witnessing the direct long-term consequences of a formation story utterly distinct from our own. We are seeing worlds that capitalized on the abundance of volatiles beyond the frost line, growing to immense proportions by rapidly vacuuming up primordial gas and retaining that initial heat and composition for eons. Their very existence is a living fossil of the solar system's earliest days. This understanding forces us to confront the true diversity of planetary architecture. It's not just that gas giants are bigger versions of Earth, they are fundamentally different types of planets, born from different recipes and processes in the same cosmic kitchen. They are a testament to the fact that the universe doesn't just create one kind of world, but an astonishing spectrum, each with its own unique history etched into its very core, each a distinct answer to the question of planetary formation. And in recognizing this profound difference, this cosmic divergence, we begin to truly appreciate the incredible variety of our own solar system, and by extension, the myriad possibilities for planetary systems across the galaxy. The what they are is inseparable from the how and where they came to be. And that, my friends, is a lesson that truly expands our cosmic classroom, inviting us to imagine what other incredible worlds await discovery. As we journeyed through the outer reaches of our solar system, from the majestic rings of Saturn to the peculiar, side-spinning Uranus and the furiously windy Neptune, we uncovered worlds of profound strangeness. Triton, with its geysers of nitrogen ice and plumes stretching into the thin atmosphere, offered us a glimpse into a cryovolcanic ballet, a testament to the dynamic forces at play even in the frigid darkness. But what do these incredible, utterly alien landscapes, these colossal fluid spheres, truly tell us about the very definition of a planet? This is where the conventional wisdom we absorbed in school about planets, solid, rocky bodies like Earth, Mars or Venus, begins to crumble under the sheer weight of cosmic reality. The gas and ice giants don't just expand our understanding, they force us to fundamentally redefine it. We've explored worlds without a surface to stand on, where the very concept of ground is a gradual transition from a gas to a supercritical fluid, then to a churning ocean of metallic hydrogen, and finally perhaps to a fuzzy core of heavy elements. Can you imagine trying to land a spacecraft on Jupiter only to have it slowly, inexorably, descend through ever denser layers, crushed by pressures that would flatten steel until it simply ceased to exist as a discrete object? It's a mind-bending thought experiment that underscores the profound difference between these giants and our familiar terrestrial home. These aren't just bigger versions of Earth. They are entirely different beasts, governed by different rules, born from different cosmic circumstances. Their immense gravitational fields, their swirling atmospheres, their internal heat engines that radiate more energy than they receive from the sun. These are characteristics that paint a picture of planetary evolution and dynamics far more complex and diverse than we ever imagined. We need to shed our Earth-centric biases and embrace the full spectrum of planetary identity. Think about it. When we speak of Earth, we envision continents, oceans, a distinct atmosphere, and a solid crust. On the Moon, it was a dusty, cratered surface. On Mars, a red, rocky desert. But on Jupiter, Saturn, Uranus, or Neptune, we're talking about giant spinning balls of fluid, where weather systems dwarf continents, where storms rage for centuries, and where the very notion of down leads not to rock but to an ever-thickening, crushing embrace of fluid matter. It's like swimming in an ocean where the water gradually becomes less like water and more like a very thick, soupy air, until it's so dense it behaves like a liquid metal, and then even denser. This isn't just a change in state. It's a change in the fundamental nature of what constitutes a world. And these giants are not solitary wanderers. Each is the heart of its own miniature solar system, a gravitational titan orchestrating a ballet of dozens, sometimes hundreds, of moons and intricate ring systems. These systems are incredibly diverse, each moon a unique world with its own story. We've seen Io, perpetually ripped apart and reformed by Jupiter's tidal forces, a volcanic inferno. We've marvelled at Europa, Ganymede and Callisto, each harbouring vast global subsurface oceans, potentially warmed by the very same tidal energies that torment Io. We've gazed upon Titan, shrouded in a thick orange haze, where rivers and lakes of liquid methane and Ethane carve landscapes reminiscent of Earth, yet utterly alien in their chemistry. And then there's Enceladus, a tiny, icy moon actively spewing plumes of water, organic molecules, and salts from its subsurface ocean directly into space. These moons challenge another fundamental assumption, that life, as we know it, requires a planet within the Sun's, quote 56, that perfect orbital distance where liquid water can exist on the surface. But Europa and Enceladus prove that stellar energy isn't the only game in town. Their internal oceans are warmed by the relentless kneading of tidal forces from their colossal parent planets. This tidal heating provides a consistent, long-lived energy source, potentially fueling hydrothermal vents on their ocean floors, creating chemical gradients, the very ingredients thought to be crucial for the origin and sustenance of life here on Earth. Imagine a deep-sea ecosystem thriving in perpetual darkness, kilometers beneath an icy shell, completely independent of sunlight, nourished by the gravitational embrace of a gas giant. It's a staggering thought, expanding the cosmic real estate where life might arise exponentially. What kind of life might exist in such environments? Would it be based on water, or perhaps something more exotic like the methane-based chemistry we see on Titan? The very question stretches our imagination and forces us to reconsider our biological definitions. Perhaps life doesn't always need oxygen, or sunlight, or even the same amino acids that form the basis of all life on Earth. The potential for weird life based on entirely different chemical principles, is a concept that moves from science fiction to plausible scientific inquiry when we look at these distant moons. The ring systems, too, are more than just beautiful ornaments. They are dynamic, evolving phenomena, composed of countless icy particles, ranging in size from dust grains to mountains. These particles are constantly colliding, clumping, breaking apart, and interacting with the gravitational pulls of the shepherd moons that carve out gaps and maintain their intricate structures. Saturn's rings, in particular, are a masterpiece of celestial mechanics, a cosmic laboratory where we can study gravitational interactions and the formation of planetary bodies in miniature. They are not static, but living, breathing parts of these giant planetary systems, whispering tales of their violent formation and ongoing evolution. Our exploration of these gas and ice giants is far from over. Missions like NASA's Juno spacecraft continue to orbit Jupiter, peering beneath its turbulent cloud tops with microwave and gravity instruments, giving us unprecedented insights into its deep interior and magnetic field. The data from Juno has already challenged our models, suggesting a more complex diffuse core than previously thought, a fuzzy core as we discussed, blurring the lines between core and mantle. Looking to the future, the Europa Clipper mission is gearing up to launch, specifically designed to investigate Europa's ocean, characterize its habitability, and scout for potential landing sites for future missions. The European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, is also on its way, with plans for multiple flybys of Europa, Callisto, and eventually orbiting Ganymede. These missions are not just about sending probes, they are about extending our senses, our curiosity, our very reach into these distant, mysterious ocean worlds, searching for the telltale signs of life. And what about Uranus and Neptune? They remain largely unexplored since the Voyager 2 flybys decades ago. Future missions to these ice giants are high on the wish list of planetary scientists, promising to unravel the mysteries of their unique magnetic fields, tilted axes and exotic atmospheric chemistry. Ultimately, the gas and ice giants teach us humility and wonder. They force us to discard our preconceived notions and embrace a universe far more imaginative and diverse than our terrestrial experiences could ever suggest. They are not just planets. They are colossal cosmic engines, cradles of potential life, and systems unto themselves, each a universe of discovery waiting to be fully unveiled. So, what didn't they teach us in school about the gas giant planets? They didn't teach us that planet is a flexible, wondrous term, encompassing worlds of swirling gas and liquid metal, worlds with internal heat sources, worlds that host oceans beneath miles of ice, and worlds that might just harbour life utterly unlike our own. They didn't teach us that our solar system is not just a collection of distinct bodies, but an intricate tapestry of interconnected gravitational dances where giants shape the fate of their moons and indeed the entire cosmic neighbourhood. We are not just exploring planets, we are redefining what it means to be a world, expanding the very boundaries of our cosmic imagination, one colossal, fluid sphere at a time. And this journey of redefinition, this quest for understanding, is perhaps the most exhilarating lesson of all. We've spent chapters dismantling what you thought you knew about planets, about water, about the very conditions necessary for life. We've journeyed to worlds where a solid surface is a myth, where oceans churn under miles of ice, and where the very fabric of a planet is a cosmic paradox, a giant, spinning ball of fluid that defies terrestrial intuition. But the profound strangeness of the gas and ice giants isn't just about their colossal scale or their exotic interiors. It's about how they fundamentally challenge our Earth-centric biases, forcing us to redefine not just what a planet is, but what life itself might entail. Think back to the International Astronomical Union's IOU definition of a planet. It must orbit the Sun, be massive enough for its own gravity to pull it into a rounded shape, and have cleared the neighbourhood around its orbit. For Earth, Mars, and our rocky siblings, this definition feels intuitive. But for Jupiter, Saturn, Uranus, and Neptune, it takes on a whole new layer of meaning, a mind-bending twist that school textbooks rarely touch. Consider that second criterion, massive enough for its own gravity to pull it into a rounded shape. On Earth, this implies a solid body, held together by chemical bonds, then sculpted by gravity. But a gas giant, it's not just a quote gangsterstry, it is gravity. Its entire existence is a constant gravitational collapse, halted only by the internal pressure of its superheated, degenerate matter. It's a sphere of fluid, not because it was once molten and cooled, but because its own immense gravity is ceaselessly trying to crush it into the smallest possible volume. This isn't a planet that became round. It's a planet whose very being is defined by its gravitational roundness, a cosmic balloon of gas and liquid held in perpetual dynamic equilibrium. It's a distinction that might seem subtle, but it speaks volumes about the fundamentally different physics at play. And what about clearing its orbit? Jupiter, with its immense gravitational dominance, has certainly cleared its path, scattering debris, flinging comets, and even shaping the asteroid belt. But it does so not as a solid bulldozer, but as a gravitational shepherd, a colossal cosmic vacuum cleaner whose presence alone profoundly alters the dynamics of the entire solar system. It's clearing is less about physical collision and more about a gravitational ballet, a dance of forces that dictates the fates of countless smaller bodies. This isn't just a bigger version of Earth, it's a different kind of astronomical object, a gravitational titan whose very nature reshapes its surroundings. But the most revolutionary shift in perspective these giants offer isn't just about the classification of celestial bodies. It's about the very concept of habitability. For generations, the search for life beyond Earth has been dominated by the Goldilocks zone, that narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface. It's a beautiful, intuitive concept born from our own experience on a world bathed in sunlight. Yet, the gas giants and their moons have utterly shattered this cozy sun-centric view. We've seen how tidal heating, that relentless gravitational squeezing and stretching from the giant planets, can generate immense amounts of internal heat. This isn't sunlight. This is deep-seated geological energy, powerful enough to sustain vast subsurface oceans of liquid water on moons like Europa, Ganymede, and Enceladus, far beyond the traditional Goldilocks zone. These aren't just puddles. These are oceans, potentially many times deeper and vaster than all of Earth's oceans combined, existing in perpetual darkness under miles of icy crust. This realization is nothing short of mind-bending. It means that the cosmic real estate suitable for life is far, far larger than we ever imagined. Instead of a narrow, sun-warmed band, we now envision a sprawling galactic tapestry, where liquid water, the essential solvent for life as we know it, can thrive in unexpected pockets throughout planetary systems, powered by the gravitational embrace of giant worlds. It's a profound paradigm shift, transforming our understanding of where life might arise and what forms it might take. And, quote 67, is the crucial next step. If life can exist in these deep, dark, high-pressure, radiation-shielded oceans, what would it look like? It wouldn't be photosynthesizing, that's for sure. Instead, we look to Earth's own extremophils for clues. The chemosynthetic organisms thriving around hydrothermal vents in our own abyssal depths, deriving energy not from sunlight, but from chemical reactions, from the interaction of superheated water with minerals. Imagine entire ecosystems built around these vents on Europa, on Enceladus, powered by the same kind of geological engine that drives life in Earth's deepest trenches. But what if life isn't even based on water? What if it uses different solvents, different chemical building blocks? Titan, Saturn's hazy moon, offers an astonishing alternative. With its thick nitrogen atmosphere, its lakes and rivers of liquid methane and ethane, and its complex organic chemistry, Titan presents a truly alien landscape. Could exotic, non-water-based life forms exist there, perhaps utilizing methane as a solvent, or engaging in entirely different metabolic processes? It's a question that pushes the very boundaries of our biological imagination, forcing us to consider that, quote, Thin 68 might be a far more diverse and resilient phenomenon than our earthbound biology has led us to believe. This isn't just about finding microscopic bugs, it's about expanding our definition of existence itself. What would the biosignatures of such, quote 69 even be? On Earth, we look for oxygen, methane, water vapor, gases associated with biological activity. But in a methane ocean or a deep anoxic subsurface sea, the signs might be entirely different. Subtle chemical imbalances, unexpected energy gradients, or even unique molecular structures that our current instruments aren't designed to detect. It's a grand cosmic detective story, and we're just beginning to understand the clues. The good news is we are actively pursuing these clues with a new generation of ambitious missions. The dreamy science of yesterday is rapidly becoming the engineering marvels of today and tomorrow. Take Europa Clipper, for instance, set to launch in the coming years. This mission is a direct assault on the mysteries of Europa's ocean. It won't land, but it will perform dozens of close flybys, swooping through the radiation belts, using radar to pierce the icy crust, mapping the ocean's depth and salinity, and searching for plumes of water erupting from the moon's surface. If these plumes exist and are accessible, Europa Clipper will be able to directly sample them, sniffing out organic molecules, salts, and other potential biosignatures. Imagine actually tasting the ocean of an alien world. Then there's JUICE, the Jupiter Icy Moons Explorer, from the European Space Agency, already on its way. JUICE will specifically focus on Ganymede, Callisto, and Europa, performing detailed observations and eventually entering orbit around Ganymede. Its instruments are designed to probe the subsurface oceans, characterize their composition, and understand the intricate interplay of geology, tides, and potential habitability across these three unique worlds. And for truly alien environments, we have Dragonfly, NASA's revolutionary rotorcraft lander, destined for Titan. This drone-like craft will hop from one location to another across Titan's surface, exploring its vast dunes, sampling its organic-rich sands, and even flying over its methane lakes. Dragonfly isn't just looking for water-based life. It's designed to explore complex organic chemistry in an entirely different liquid environment, searching for the precursors or even the manifestations of exotic life. It's a mission that embodies the spirit of embracing the truly alien. Beyond these, concepts for future missions are already being developed. Imagine an Enceladus Orbilander, a spacecraft that could orbit the tiny moon, then land, not just to sample its plumes, but to drill into its ice and potentially explore the ocean directly. Or imagine probes designed to brave the crushing pressures of Jupiter's atmosphere, descending deep into its layers to understand the chemical processes that drive its weather and internal dynamics. These aren't just science fiction fantasies. They are the logical next steps in our scientific exploration, driven by the profound questions raised by the gas giants. The implications of these explorations are staggering. If we find evidence of life, even microbial life, in the subsurface oceans of Europa or Enceladus, or exotic chemistry hinting at life on Titan, it would fundamentally alter our understanding of our place in the cosmos. It would suggest that life is not a unique terrestrial anomaly, but perhaps a common cosmic phenomenon, arising wherever the right conditions, liquid solvent, energy, and chemical building blocks, converge, regardless of sunlight or surface conditions. These giant planets, once seen as mere cosmic bullies, far too cold and inhospitable for life, have unveiled a hidden universe of possibilities. They teach us humility, forcing us to shed our Earth-centric biases and embrace the boundless diversity of the cosmos. They remind us that the universe is far stranger, far more creative, and far more awe-inspiring than our wildest dreams. The lessons they offer extend beyond astronomy and into philosophy, challenging us to redefine not just planet or life, but our very understanding of existence itself. The journey of discovery is far from over. In fact, with these giants as our guides, it feels like it's only just begun. We've journeyed together, haven't we? From the swirling behemoth of Jupiter to the ringed elegance of Saturn, then out to the enigmatic ice giants, Uranus and Neptune. We've peeled back their atmospheric layers, dove into their exotic interiors, and marvelled at the sheer scale of their power. But perhaps the most profound revelation, the one that truly reshapes our cosmic imagination, isn't just about what these giants are, but what they allow to be. They aren't just colossal balls of gas and ice. They are cosmic architects sculpting environments where life, utterly unlike anything we once assumed, might thrive. Think back to Europa, Ganymede, Callisto, and Enceladus. Worlds with vast hidden oceans of liquid water, warmed not by the distant sun, but by the relentless gravitational ballet of their titanic parents. On Earth, life is fundamentally tied to the sun. Photosynthesis forms the base of almost every food chain. Our very existence, from the air we breathe to the food we eat, is a solar product. But in these dark subsurface seas, shielded from the harsh radiation belts of Jupiter and Saturn, sunlight is an alien concept. Here, life, if it exists, would be a creature of the deep, a testament to chemosynthesis, drawing energy from hydrothermal vents, much like the ecosystems found at Earth's own abyssal trenches. Imagine a world where the very idea of, quote, 73 and, quotiasters 74 is meaningless, where the sky is an eternal ceiling of ice kilometers thick, where the only light comes from the bioluminescence of strange creatures or the fiery glow of volcanic vents on the ocean floor. What kind of organisms would evolve in perpetual darkness, under immense pressure, feeding on chemical gradients rather than photons? Would they be microscopic, forming vast mats of extremophilic bacteria? Or could complex multicellular life forms evolve, perhaps resembling our own deep-sea denizens, but with adaptations we can barely conceive? The implications are staggering. It means the stargazers, quote, 75. That narrow band around a star where liquid water can exist on a planet's surface is no longer the sole arbiter of habitability. The universe, it seems, has far more hospitable real estate than we ever dared to dream. But our redefinition of life doesn't stop with water. Remember Titan, Saturn's largest moon. A world swathed in a thick, hazy nitrogen atmosphere, home to lakes, rivers, and seas not of water, but of liquid methane and ethane. This is where our terrestrial biases truly get a workout. For us, water is life's solvent, its indispensable medium. But what if life could emerge and thrive in a cryogenic liquid at temperatures hundreds of degrees below zero? Picture a different kind of, quote, 76. On Titan, methane evaporates from lakes, forms clouds, and precipitates as rain. Rivers of methane carve channels into the icy landscape, flowing into vast liquid hydrocarbon seas. Could cells form in such a solvent? What would their membranes be made of, if not lipids designed for water? What kind of biochemical reactions could unfold in such an environment? Scientists are actively exploring hypothetical, quote, 77, cell-like structures that could form in liquid nitrogen, or perhaps, quote, 78, in liquid methane, potentially using acetylene as a food source. This isn't science fiction, it's the cutting edge of astrobiological thought, driven by the profound strangeness of worlds like Titan. If life on Earth is carbon-based and water-dependent, what if life elsewhere is silicon-based, or uses a different solvent entirely. Titan forces us to consider that Quote-Sevenian might be a far broader, more diverse phenomenon than our single example suggests. It might not breathe oxygen, might not require sunlight, might not even be based on DNA and proteins as we know them. It could be, Quote-80, a truly alien biology that challenges our most fundamental assumptions. And the gas giants, through their moons, are our primary laboratories for exploring these mind-bending possibilities. These explorations of potential life, however exotic, inevitably bring us back to the giants themselves and force us to confront another fundamental question. What is a planet? We started this journey with the conventional definition ingrained in our minds from school: a celestial body orbiting a star massive enough to be rounded by its own gravity and having cleared its orbital neighbourhood. But the gas giants, particularly Jupiter, throw a wrench into that seemingly neat classification. Jupiter, as we've learned, has no solid surface, no ground to stand on, no bedrock to drill into. It's a giant spinning ball of fluid, gradually transitioning from gas to supercritical fluid to a churning ocean of metallic hydrogen. Where does the Quote-81 end and the Quote-82 begin? It's a continuum, a gradient of increasing density and pressure. If you could somehow descend into Jupiter, you wouldn't land, you'd just sink, your surroundings getting progressively denser and hotter until you were crushed by the unimaginable pressures. This challenges our terrestrial intuition, which is so accustomed to a distinct interface between air and land or sea. And what about its core? The Juno mission has suggested Jupiter's core isn't a neat solid sphere, but rather a C-83 diffuse mix of heavy elements and metallic hydrogen, perhaps larger and less distinct than models previously predicted. This Quote-84 hints at a planet that is still mixing, still evolving, a dynamic entity where the very concept of a Quote-85 vase is less about a solid boundary and more about a region of increased concentration. This fluid nature, coupled with their sheer mass, pushes the gas giants towards a fascinating boundary in stellar classification. We call them planets, but what separates a gas giant from a brown dwarf, a Quote-86, that isn't massive enough to ignite hydrogen fusion in its core, but is still far more massive than any planet. The distinction, it turns out, is less about composition and more about mass and origin. Brown dwarfs are typically thought to form like stars, collapsing directly from a gas cloud, albeit a smaller one. Planets, even gas giants, are thought to form within a protoplanetary disk around a star, accreting material. But there's a grey area. Some Quote-187 found orbiting other stars are so massive they blur the lines, making us wonder if they are truly planets or very low-mass brown dwarfs. The existence of such massive fluid worlds, with their immense gravitational fields and their profound influence on their systems, compels us to broaden our definition of a planet. Is it simply about orbiting a star? What about, then, Quote-Anoanteols that wander interstellar space, having been ejected from their birth systems? Are they still planets if they don't orbit a star? What about objects like Pluto, which was reclassified because it hadn't Quote-89? The gas giants, in their sheer magnitude and unique internal structures, force us to acknowledge that our solar system is a cosmic zoo of diverse celestial bodies, each deserving of study on its own terms, rather than being squeezed into rigid Earth-centric categories. And then there's the grander perspective. Our understanding of the gas giants has profoundly reshaped our view of planetary system formation. The grand tack migration of Jupiter, its early inward then outward journey, wasn't just a quirky detail. It was a cosmic billiard shot that literally sculpted our inner solar system. It cleared out the early asteroid belt, preventing a deluge of impacts on the terrestrial planets, and likely delivered some of the water that makes Earth habitable. Without the gas giants, our solar system would be a vastly different, perhaps far less hospitable place. They are not just bystanders, they are central players in the cosmic drama. This understanding extends far beyond our own solar system. As we discover thousands of exoplanets, a significant portion are, quote 91, gas giants orbiting incredibly close to their parent stars. The insights we gain from our own Jupiter and Saturn, even though they are much colder and more distant, are invaluable for interpreting data from these alien worlds. We're learning that planetary systems are incredibly diverse, with architectures often wildly different from our own. Are gas giants with habitable moons common around other stars? Could these, quote 92, be the most prevalent abodes for life in the galaxy? This is a question that future telescopes, like the James Webb Space Telescope, are just beginning to probe. The journey into the gas giants has been one of shedding assumptions. We've learned to look beyond the Goldilocks zone for habitability. We've learned to challenge the very definition of a quote 94 or a quote 95. We've been asked to stretch our minds to contemplate life in methane, or oceans beneath miles of ice, warmed by tidal forces. These colossal worlds, so utterly alien to our terrestrial senses, are not merely distant curiosities. They are fundamental teachers. They teach us that the universe is far more imaginative than we are, far more diverse, and far more abundant with possibilities than our earthbound perspectives ever allowed us to believe. What they didn't teach you in school, perhaps because they couldn't, is that the gas giants are not just big planets. They are cosmic paradoxes, challenging our definitions of matter, energy, and life itself. They are colossal laboratories of extreme physics and chemistry, pushing the boundaries of what we thought possible. They are the silent, powerful orchestrators of our solar system's history, and potentially the most common cradles for life in the cosmos. As we conclude this exploration, perhaps the most important lesson isn't just about the science, but about the spirit of inquiry itself. It's about the willingness to look at the seemingly familiar, a planet, and realize it's something profoundly strange and new. It's about asking what if and why not. It's about letting go of our preconceived notions and embracing the wonder of the truly alien. Because in doing so, we don't just learn about distant worlds, we learn about the boundless capacity of the universe and our own place within its magnificent, bewildering tapestry. The gas giants, in their immense, swirling glory, remind us that the greatest discoveries often lie just beyond the edge of our current understanding, waiting for us to dare to look. And in doing so, we don't just expand our knowledge, we expand our very definition of existence. We've journeyed through the swirling depths of Jupiter, navigated the icy rings of Saturn, and plunged into the frigid, turbulent hearts of Uranus and Neptune. We've explored moons bathed in radiation, moons with subsurface oceans, and moons with hydrocarbon seas. Our understanding of what constitutes a sus quote 98 has been fundamentally reshaped, stripped of its Earth-centric biases. But as we stand on the precipice of these future missions, Europa Clipper poised to sniff out life's chemicals, Dragonfly preparing to hop across Titan's methane dunes, Juice set to unravel the secrets of Ganymede, Callisto and Europa, we must now confront an even more profound challenge, redefining quote 90 Nustans itself. What exactly are we looking for when we talk about quote 100 dwelled on these utterly alien worlds? Our terrestrial intuition, honed by billions of years on a water-rich, oxygen-infused planet under a nurturing sun, whispers of liquid water, organic molecules, and a stable energy source. And indeed, these are the primary ingredients our robotic emissaries are designed to detect. But is that all there is? Is life, in its cosmic entirety, confined to the precise chemical recipes and environmental conditions that brought us into being? The gas giants and their moons, in their spectacular diversity, compel us to wonder if the universe might hold far more exotic forms of biology than we can currently imagine. Consider Titan. Its lakes and rivers flow with liquid methane and ethane, not water. Its atmosphere is thick with nitrogen, laced with complex organic molecules. Could life here use methane as its solvent, perhaps even breathing hydrogen instead of oxygen, and exhaling methane? The chemistry would be profoundly different from anything we know. Imagine organisms with cell membranes made not of phospholipids, but of entirely different, cryogenically stable compounds, metabolisms that extract energy from the chemical gradients of hydrocarbons, rather than water-based redox reactions. This isn't just science fiction, it's a legitimate scientific inquiry, pushing the boundaries of what we conceive as possible. When we search for biosignatures, we're essentially looking for evidence of a sustained, ordered system that uses energy to maintain itself, replicate, and evolve. On Earth, these signs include specific organic molecules, amino acids, nucleotides, isotopic fractionation, life often prefers lighter isotopes, and complex structures that defy simple geological explanation. But what if life on Titan leaves behind a different set of chemical fingerprints? What if the fossils of a methane-based organism look nothing like the carbonaceous remnants we find in ancient Earth rocks? This is the profound strangeness we must embrace. We're not just looking for life as we know it, we're learning to look for quote 104. This challenge forces us to acknowledge our inherent quote 105 and quote 106 carbon, with its 4 valence electrons, forms incredibly stable and diverse bonds, making it the backbone of every known organic molecule. Water, with its unique polarity and solvent properties, is indispensable for all known biological processes. But in the extreme environments of the outer solar system where temperatures plummet and pressures soar, could other elements or compounds take on these roles? Could silicon, just below carbon on the periodic table, form the basis of exotic polymers in a different solvent? Could liquid ammonia, abundant on some icy bodies, serve as a solvent for life at much colder temperatures? These are not idle musings. They are essential questions that expand our search for extraterrestrial existence. Our understanding of habitability itself has undergone a staggering transformation thanks to the gas giants. For decades, the R-107, the region around a star where temperatures allow liquid water to exist on a planet's surface, was the primary yardstick for habitability. Too close, and water boils away. Too far, and it freezes solid. Earth, Mars, and Venus are the poster children for this concept. But what do Jupiter's moon Europa, Saturn's moon Enceladus, or even Jupiter's own Ganymede teach us? They teach us that the Goldilocks zone is at best a single chapter in a much larger, more diverse cosmic story. These moons reside far beyond the traditional Goldilocks zone of the Sun, where surface temperatures are brutally cold, often hundreds of degrees below freezing. Yet beneath their icy shells, vast oceans of liquid water persist. How? Through the relentless, invisible hand of Wamgai tidal heating. The immense gravitational pull of their colossal parent planets, combined with the gravitational tugs of neighbouring moons, stretches and squeezes these satellites. This constant kneading generates immense friction within their interiors, dissipating as heat. It's like repeatedly bending a paperclip until it warms up, but on a planetary scale. This internal furnace melts ice, sustains liquid oceans, and potentially drives hydrothermal activity on the seafloor, providing both a solvent and an energy source for life, entirely independent of the sun's warmth. This realization represents a paradigm shift. It means that the universe's habitable real estate is far more extensive than we ever dared to imagine. Instead of just a narrow band around stars, we now recognize as just, quote, extending far into the frigid outer reaches of planetary systems. Every gas giant and ice giant, with its retinue of icy moons, becomes a potential harbinger of life. This profound insight multiplies the number of potentially life-bearing worlds in our own solar system, and by extension, across the galaxy, exponentially. And this isn't just about moons. The principles we've learned from our gas and ice giants have profound implications for exoplanet research. As telescopes like JWST and future missions probe the atmospheres of distant worlds, we're encountering a bewildering array of planetary types. Hot Jupiters orbit perilously close to their stars, often tidally locked, their atmospheres superheated. Could their powerful gravitational field still tidally heat any close-in moons, creating subsurface oases even in such extreme environments? Or what about the more common super-Earths and mini-Neptunes, worlds larger than Earth but smaller than Neptune? Many of these worlds are thought to have deep, dense atmospheres, perhaps even global oceans of supercritical fluids, a state where liquids and gases become indistinguishable. Could life exist within these endless churning fluid envelopes, swimming in an ocean where the water gradually becomes less like water and more like a very thick, soupy air, much like our theoretical descent into Jupiter? The lessons from our own gas giants are vital here. They teach us to look beyond simplistic models. A super-Earth might not be a larger version of our home planet. It could be a water world with an ocean thousands of kilometers deep, under pressures that create exotic phases of water, or a world with a dense hydrogen-helium envelope making its surface as indistinct as Jupiter's. Could be an ice giant in miniature, with a slushy, electrically conductive interior generating its own magnetic field, protecting a deep, supercritical ocean from stellar radiation. The very concept of a rare quote 115 becomes problematic, much as it is on Jupiter. This expansive view of habitability also redefines our search for intelligent life. If life can arise in such diverse and unexpected corners of the cosmos, then the statistical probability of its existence elsewhere skyrockets. We are not just looking for Earth 2.0, we are opening our minds to the vast imaginative possibilities of the universe. The gas giants, once dismissed as mere gravitational bullies or uninteresting, uninhabitable gas balls, have become cosmic architects shaping the solar system, providing the conditions for life far from the sun, and challenging our most fundamental assumptions about existence. The journey through the realm of the gas giants is, in essence, a journey into the profound strangeness of the cosmos. It's a humbling experience, forcing us to shed our Earth-centric biases and embrace a universe far more imaginative and diverse than our textbooks ever suggested. We are learning that the universe doesn't operate on our terms, but on its own magnificent, often counterintuitive physical laws. Every new discovery, every piece of data from a distant probe chips away at our terrestrial myopia, revealing a tapestry of possibility that is both exhilarating and slightly unsettling. The gas giants, with their swirling atmospheres, their metallic hydrogen hearts, their ring systems and their life-sustaining moons, are not just distant celestial bodies. They are cosmic laboratories, challenging us to redefine our most cherished scientific concepts. They stand as colossal monuments to the universe's boundless creativity, whispering tales of alternative chemistries, hidden oceans, and perhaps entirely new forms of existence. As we look to the future, to the missions that will drill into Europa's ice or float across Titan's lakes, we do so with a renewed sense of wonder and intellectual humility. We are no longer just exploring planets. We are exploring the very definitions of planet, of life, and of our place in a universe that is far grander, far stranger, and infinitely more fascinating than anything they could have possibly taught us in school. The gas giants, it turns out, hold the keys to unlocking not just the secrets of our solar system, but the potential for life across the cosmos. And that, dear cosmic explorers, is a truth as mind-bending as a journey to Jupiter's core.